Hello everyone. Welcome to the 8th session on Semiconductor Fundamentals. In this session, I will be discussing on Schottky diodes. The Schottky diode is a special purpose device that is named after the German physicist Walter Schottky. Unlike other diodes that rely on a semiconductor to semiconductor junction, the Schottky diode is comprised of a semiconductor to metal contact. With such a design, the Schottky diode exhibits two major advantages over traditional diodes. First, they have very fast switching times, perhaps in several orders of magnitudes of improvement. Second, they exhibit relatively low turn-on voltages. Instead of a 0.6 to 0.7 volts seen across the silicon junction diode, a Schottky diode may turn on with as little as 0.2 or 0.3 volts. Consequently, Schottky diodes are used when very fast switching speed and or minimizing forward voltage drops are important. Let us now have a look at the construction of a Schottky diode. In Schottky diodes, a metal to semiconductor junction is formed between a metal and a semiconductor, thereby creating what is called as a Schottky barrier. Typical metals used are molybdenum, platinum, chromium or tungsten, and certain silicides such as palladium silicide and platinum silicide, whereas the semiconductor would typically be of N-type silicon. Titanium silicide and other refractory silicides, which are able to withstand the temperature needed for source or drain annealing in CMOS processes, usually have too low a forward voltage to be useful. So, processors using these silicides therefore usually do not offer Schottky diodes. The metal side acts as the anode and the N-type semiconductor acts as the cathode of the diode, meaning conventional current flow from the metal side towards the semiconductor side and not in the opposite direction. This Schottky barrier results in both very fast switching as well as low forward voltage drop. The choice of the combination of the metal and semiconductor determines the forward voltage drop of the diode. Both N and P-type semiconductors can develop Schottky barriers. However, the P-type typically has a much lower forward voltage drop. Though the reverse leakage current increases dramatically with decrease in the forward voltage drop, it cannot be too low. So, the usually employed range is about 0.5 to 0.7 volts, and P-type semiconductors are employed very rarely. We know that with increased doping concentration of the semiconductors, the width of the depletion region reduces. Below a certain width of the depletion region, the charge carriers can tunnel through the depletion region. At very high doping levels, the junction does not behave as a rectifier anymore and becomes an ohmic contact. This can be used for simultaneous formation of ohmic contacts and diodes, as a diode will form between the silicide and lightly doped N-type region, and an ohmic contact will form between the silicide and the heavily doped N or P-type region. Lightly doped P-type regions pose a problem, as the resulting contact has too high a resistance for a good ohmic contact, but too low a forward voltage and too high a reverse leakage current to make a good diode. As the edges of the Schottky contact are fairly sharp, a high electric field gradient occurs around them, which limits how large the reverse breakdown voltage threshold can be. To solve this issue, various strategies have been employed, such as guard rings and overlaps of metallization to spread out the field gradient. Now, having discussed the construction, let us move on to discuss the working principle of the Schottky diode. I'll start with the first condition, which is also called as the unbiased Schottky diode condition. The free electrons present in the N-type semiconductor will move from N-type semiconductor to the metal during the joining of the metal and N-type semiconductor. This results in the production of equilibrium state. When free electrons move across the junction, it provides an extra electron to the atoms present in the junction. Due to this, atoms present in the metal junction receive an extra electron. The atoms at the semiconductor side junction lose electrons and become positive ions. Similarly, in the metal junction, atoms will gain an extra electron and become negative ions. Hence, this will result in production of positive ions at the semiconductor side and negative ions on the metal side of the junction. A depletion region will then be formed when these positive and negative ions come together. In unbiased Schottky diode, only a very small number of free electrons will flow from the semiconductor to the metal side. Free electrons will need a greater supplied energy than their built-in voltage to overcome this barrier. Continuing to the second biasing condition, which is the forward biasing condition for the Schottky diode. When a positive terminal of the battery is connected to the metal and negative terminal is connected to the N-type semiconductor, the diode is said to be forward biased. When the forward applied voltage is greater than 0.2 volts, free electrons from the semiconductor side can move through the junction barrier towards the metal side. This results in flow of current that is typical for most of the diodes available. Moving on to the third and the last biasing condition, the reverse biasing condition. If the negative terminal of the battery is connected to the metal and positive terminal is connected to the N-type semiconductor, the diode is said to be reverse biased. If a reverse bias voltage is increased, the width of the depletion region increases and therefore the current flow decreases. However, there will be a small amount of leakage current flowing across the device even under reverse biased mode. However, if the reverse bias voltage continues to increase, this can eventually break down the barrier and a large reverse breakdown current starts flowing through the device. Now, moving on to the next topic in line, which is the VI characteristics of the Schottky diode. We are looking at the VI characteristic curves for a Schottky diode. In the graph shown, the y-axis signifies the current flow and the x-axis denotes the voltage applied across the Schottky diode. The VI characteristics of the Schottky diode are almost similar to that of a simple PN junction diode. However, the forward voltage drop of the Schottky diode is very low when compared to the PN junction diode and ranges between 0.3 volts to 0.5 volts. The barrier of the forward voltage drop is made of silicon and is proportional to the doping concentration of the N-type semiconductor. It should also be noted that due to the high concentration of current carriers, the VI characteristic curve of the Schottky diode is considerably steeper in the forward bias condition. Moving on to some of the very important parameters one must consider while designing any circuit that includes a Schottky diode. Starting with the very first and the most important one, which is the reverse recovery time. The most important difference between the PN diode and the Schottky diode is in fact the reverse recovery time. In a PN diode, the reverse recovery time can be in the order of several microseconds to less than 100 nanoseconds for fast diodes, and it is mainly limited by the diffusion capacitance caused by minority carriers accumulated in the diffusion region during the conducting state. Schottky diodes are significantly faster since they are unipolar devices and their speed is only limited by the junction capacitance. The switching time for the Schottky diodes varies somewhere between 100 picoseconds for the small signal diodes and up to tens of nanoseconds for special high capacity power diodes. With PN junction switching, there is also a reverse recovery current which is in high power semiconductor brings increased electromagnetic interference noise. With Schottky diodes, switching is essentially instantaneous with only a slight capacitive loading which is much less of a concern. It is often said that the Schottky diode is a majority carrier semiconductor device. This means that if the semiconductor body is a N-type doped material, only N-type carriers play a significant role in the normal operation of the device. These majority carriers are quickly injected into the conduction band of the metal contact on the other side of the diode to become free-moving electrons. Therefore, there will not be any slow and random recombination of N and P-type carriers, so that this diode can cease conduction much faster than an ordinary PN rectifier diode. This property in turn allows a small device area, which also makes for a faster transition. This is another reason why Schottky diodes are useful in switching mode power converters. The high speed of the diode means that the circuit can operate at frequencies in the range of 200 kHz to 2 MHz, allowing the use of a small inductors and capacitors with greater efficiency than would be possible with other types of diodes. Moving on to the second parameter at hand, the forward voltage drop. The voltage drop to turn on a forward biased diode is the forward voltage drop. It varies according to the different diodes. For Schottky diode, typically the turn on voltage is assumed to be around 0.2 volts. Moving on to the third parameter, reverse breakdown voltage. The particular amount of reverse bias voltage after which the diode breaks down and starts conducting in the reverse direction is called reverse breakdown voltage. Reverse breakdown voltage for Schottky diode is around 50 volts. Coming to the last parameter at hand, we have the reverse leakage current. It is the current conducted from the semiconductor device in reverse biased condition. In the Schottky diode, increasing the temperature will significantly increase the reverse leakage current. Now we move on to the limitations of Schottky diodes. The most evident limitation of Schottky diode are their relatively low reverse voltage ratings and their relatively high reverse leakage currents. For silicon to metal Schottky diodes, the reverse voltage is typically 50 volts or less. Some higher voltage designs are also available with reverse voltages typically about 200 volts. Since the reverse leakage current increases with temperature, it leads to a thermal instability issue. This often limits the reverse voltage to well below the actual rating of the device. While higher reverse voltages are achievable, they would present a higher forward voltage compared to other types of standard diodes. Such Schottky diodes would have no advantage unless great switching speeds are required. We now move on to the last topic in the discussion, the applications of Schottky diodes. The first one we have at hand is the voltage clamping. While standard silicon diodes have a forward voltage drop of about 0.6 volts and germanium diodes have 0.2 volts, Schottky diodes voltage drop at forward biases of around 1 milliampere is in the range of 0.15 volt to 0.46 volt, which makes them useful in voltage clamping applications and prevention of transistor saturation. This is due to the higher current density in the Schottky diode. The second application is reverse current and discharge protection. Because of the Schottky diode's low forward voltage drop, less energy is wasted as heat, making them the most efficient choice for applications sensitive to efficiency. For instance, they are used in standalone or off-grid photovoltaic systems to prevent batteries from discharging through the solar panels at night. They are also called as blocking diodes. Continuing to the third application, we have the switched mode power supplies. Schottky diodes are also used as rectifiers in switched mode power supplies. The low forward voltage and fast recovery time leads to increased efficiency. They can also be used in power supply switching circuits in products that have both an internal battery and a mains adapter input. However, the high reverse leakage current presents a problem in this case, as any high impedance voltage sensing circuit will see the voltage from the other power source through the diode leakage. Moving on to the last application at hand, we have the sample and hold circuits. Schottky diodes can also be used in diode to bridge based sample and hold circuits. When compared to regular PN junction based diode bridges, Schottky diodes can offer advantages. A forward bias Schottky diode does not have any minority carrier charge storage. This allows them to switch more quickly than regular diodes, resulting in lower transition time from the sample to the hold step. The absence of minority carrier charge storage also results in a lower hold step or sampling error, resulting in a more accurate sample at the output. Well, that brings us to the end of this session. To summarize, this session provided a brief introduction to the Schottky diode, followed by its construction, working principle, VI characteristics, limitations, and applications. I hope that you found this video informative. Thank you for watching. Have a good day.